Right, so my 420 project is called Auto-DRS, which is basically about classifying runouts in cricket. So we want to find whether the stumps were hit first or the batsman crossed the crease first. And it's a complex problem because the background is complex, there's a lot of variation, bodies involved, there's a lot of occlusion, so it's not easy. Moreover, there's other constraints that we must adhere to. For example, ideally we want to capture low FPS video because high FPS video has storage and processing costs. So perhaps we could use something like super slow-mo, use a pre-trained open source implementation, which basically uses a unit-like architecture to perform temporal interpolation between frames to artificially slow it down. We also want a process to be robust. So I tried SIFT, but SIFT is not really robust in this case. So we can try to track motion, try to see which key points are moving the most. But the problem is we don't get a lot of key points on the edge of the bat, and so that's not very good to detect whether the batsman crossed the crease. And also there's a lot of noisy outlier key points that don't really add value. So it's hard to localize exactly where the batsman is at. There is also a significant data constraint because in a reasonable amount of time I was only able to find and annotate 33 clips, and 28 of them were outs and only 5 of them were not outs. So there's a severe class imbalance that we must somehow work around. Something like logistic regression gets a 97% accuracy, but it's just way too many parameters. And even if we enforce sparsity, it's learning really specific locations, so it's not really giving us translational invariance, which is something really important for a robust process. We could use something like PCA for dimensionality reduction, but we're learning eigenimages at that point, and that's still parameters in some sense. We also want our reporting to be interpretable. So something that really works well is template matching, which if we can do on an image parameter at multiple scales, we get a good bounding box exactly, and we can see which template was matched. Although this only works well in 56% of the cases, so this is not really robust to a lot of other. It doesn't generalize well. Although it's a good thing to keep in mind. So perhaps we should formulate the problem differently. First of all, we want our parameters to be small, the number of parameters to be small, and we want data to be more. So it'll be good to have a model that uses frames instead of a bunch of frames and clips. Also, instead of predicting outs and not outs, perhaps we can predict whether the stumps were hit or not and whether the batsman is in crease or not. And by doing this, we get a lot more data and we get a much better problem. The class imbalance is still significant, but it's much smaller than it was before. So with this formulation, we can obviously already do something really simple, like we can threshold the color to see the red levels because the stumps light up red when the stumps are hit. So we can do this, and this gives us a 76% baseline accuracy, which is still pretty good. So we tried a bunch of things and they work well reasonably. We get around 70-75%, but maybe we can get more invariance to noise, brightness, translation using deep learning. More importantly, using this super slow-mo paper, what I found inspiring was they use optical flow as a way to encode motion. And perhaps if we do that, we extract the frames and the flow by optionally, slowing it down using a pre-trained model, and then we can feed it into these two separate CNNs because we don't want to compete a lot given the class imbalance. Then we have 1D signals for frame-wise probabilities, and perhaps using optical flow, our CNN can, get segmentation for free and learn faster and better and using fewer parameters. And then we can pass it to a decision algorithm, which basically just checks which crossed which line first to see, make a final decision. And we get really good results. We get over 95% F1 score on both test and validation on all models. And we get 100% classification accuracy for outs and not outs because we only really care about the ordering. If the stumps are hit first or, batsmen cross the crease first. So we covered a bunch of these techniques, and as expected, deep learning is the most robust to a lot of these outliers. And our major contribution was using optical flow with the CNN in this particular problem, and it hasn't been done before to the best of my knowledge. Let's go to a quick demo now.